Hello, everyone, and welcome to our latest edition of our TechXchange webinar. We very much appreciate that you take the time today for this 30-minute session. My name is Daniela, and I will guide you through this presentation. But before we begin, here are a few details. This webinar is live, and it will be recorded. All microphones are muted. And if you have any questions, there is the button below on your screen that you can type in your questions anytime. We will address them at the end of the session. If we run out of time, we will follow up with you after the webinar. So if you could include your name, we can reach out to you directly. In our TechXchange webinars, we aim to bring expert insights and the latest updates on reciprocating compressor technology and services. Today, we will focus on digital solutions. Here are the key takeaways that you can expect from this session. Why the early failure detection of compressor components is so precise through segmented analysis, how data-driven decisions can increase mean time between overhauls, and how digital tools and OEM expertise strengthen operator teams on site. I'm happy to introduce you the two speakers who will give you those insights. So we have first Vitaly Tatarinov, Product Manager Services. He brings over 14 years of experience in the gas compression industry, with deep expertise in the design, calculation, and implementation of compressor upgrade and revamp solutions. Joining him, we have Philipp Bolschner, our digital product manager. He's been with the company for over 3 years, leading the development and release of cloud-based monitoring solutions. Philipp brings over a decade of experience in creating digital solutions across various tech companies. So let's get started. I hand over to you, Vitaly, for an introduction into reliability and the evolution of maintenance strategies.
Thank you, Daniela. On a very high level, compressor unit is a system which effectively consists of compressor itself, usually electric motor as a driver. It has a piping and auxiliaries to supply and take the compressed gas away. It also has skids for lubrication and cooling water, instrumentation, and other auxiliary subsystems. From reliability point of view, on this level, they all can be regarded as links in a chain when reliability of each component governs effectively reliability of the whole compression unit. When we go one step down, so on a level of a compressor, the same scalable approach basically applies. Reciprocating compressor, it's a combination of components, and these components, they are performing different function. They can be classified in several different ways. One usually can be regarded as differentiating those components to those which are in contact with a compressed media, so-called gas-wetted components. Primarily, they include components of cylinder assemblies and those components which are not, at least in a normal operation, including components of motion work and frame. The second possible classification is based on expected or normal lifetime of these components, differentiating between capital parts and wear parts. The latter normally define scheduled intervals of maintenance. But regardless the way how these components are classified, important is that they do different functions, respectively they may have different failures, and the way how components are failing, so failure modes, will also be different. And to address that, we would need to come up with a certain maintenance approach and strategy. But at this point, what cannot be overstated is that information about actual performance of these components is never in excess, it's never necessary, and as development of maintenance strategy proves, it's one of the very important trends to optimize a strategy, simply because performance of component. It does not stay fixed in a time. Compressor is subject to varying pressures, loads, gas compositions, maintenances itself are interventions which would require basically a change in the performance of those components. As an overview of maintenance strategy, and usually it starts with the least advanced one, with the reactive. Because these strategies, they have been developed also as assets in industry developing. So reactive is one, of course, when failure is fixed only when a component breaks. And also in theory, or that can give you the highest lifetime of components. Such approach has, of course, downsides of unscheduled, unplanned outages that can lead to the higher costs of maintenance and need to fight consecutive damage of your compressor. On the other extremity, we have a preventive maintenance. That is when compressor asset is maintained in a fixed interval of time. And this approach is very useful for certain types of failures, especially those which have predictable development in time, such as via failure modes of sealing components, for example, or valves. However, it's not universal, and some failure modes are actually not addressed by this approach. That leads to the next one, much more informed approach, which is called condition-based, when the performance of certain component is tracked, usually in real time, and based on indicators, the decision is made to maintain a component, replace it, or refurbish in a certain way. And these strategies, these approaches, they are not optimum when they applied on their own and alone. And this was one of the trends in the compressor industry and the industry in general, with so-called reliability-centered maintenance, started in 70s, still actively development, which says that the combination of this method is something which is appropriate. But the second big trend which is going is related to first availability of digitalized data about performance of components with this implementation of condition monitoring techniques and advances in pattern recognition, artificial intelligence. These two aspects allow actually in automatic way to first identify failure mode, and second, with a certain accuracy, make a prediction how long compressor or component performance will remain acceptable for an operation. That can bring us to much better and more informed decisions. And to show tools with which it's done, I would like to hand over to Philip.
Thank you, Vitaly, and hello everyone. I will talk today about how early failure detection on the compressors using a segment analysis can help you to extend the mean time between the overhauls. To build a strong maintenance strategy, we offer here a range of solutions from condition-based monitoring to predictive technologies. Our cloud-based solutions, Up Insights, for example, gives you an overview of the compressor condition based on purely PLC data. Next, we have the Up Detect. Here, with a minimal investment, operators gain really detailed insight at the component level of the compressor, helping detect issues early. And then on the top, we move forward to prediction. Here we have our Prognost NT. It's our 360-degree condition monitoring system with machine protection. And with its newest model, it can even calculate the remaining useful lifetime of key components. But today, our focus is on our latest solution. It is the Up Detect. It's a cost-effective and also easy to install solution that gives you as an operator a clear view of the compressor health and how long the components could last or if they are needed to be changed. Here's a quick overview of how Up Detect works. So let's take, for example, a two-throw compressor as an example. So depending on which failures you want to detect or what issue your machine has, the sensor configuration can be defined at the beginning of the installation. These sensors are then connected to our latest collection unit. It is in the X area certified and is also designed to be installed close to the compressor to also minimize the whole cabling effort. The collected signals are then processed and sent to our edge device, which is in the safe area, which then transmits the data via one-way connection to the cloud for the analysis. In the cloud, the data is then visualized in our monitoring suite, accessible, of course, from anywhere, but it's not only you as an operator has access to it, but also our support team could help you with any questions, as they could also connect to it. The sensor setup depends on the compressor type and its typical failure modes. With a fully equipped system, UpDetect can identify a really wide range of issues. For example, in the cylinder, we can detect leakage or overpressure, but we can also identify component looseness, for example, between the crosshead and the piston rod. But as well, we can detect wear or breakage of rider rings. Today, I want to focus on the 36 segment analysis. This technique is used in condition monitoring for recipe compressors to detect mechanical anomalies during the operating cycles. It's a proven technique for many years for detecting failures in recipe compressors. So it's applied in both our UpDetect and also in our Prognost NT. For this, we need a speed data and the vibration sensors placed on the crosshead and its cylinder. And looking at this horizontal compressor equipped with the setup, we can capture and analyze the complete internal movement of the compressor. And the installed sensors, they provide the raw data from each revolution of the compressor. This raw data is then divided into 36 equal angular segments, each representing 10 degrees of the crankshaft rotation. And then segmenting the cycle this way enables a high resolution tracking of vibration throughout the entire mechanical process. And then depending on the area being monitored, the different types of analyzers can be applied to each segment. So we get a when value per segment. And we are using techniques like RMS, root mean square, or zero to peak to extract here meaningful value from the raw signals. And then this makes it possible to define the different thresholds for each segment, enabling precise detection of abnormal behavior at the specific point in the compressor evolution. Here you see we get every minute then this kind of an update showing whether any segment threshold has been violated or not. While this gives you a quick snapshot, it doesn't always show you how things evolve over time. And this is the reason to get here deeper insight, we're using a different visualization method. For this, we use a heat map. The x-axis represents the 36 angular segments, and the y-axis represents the time. And here you can see it makes it easier to spot significant changes in the compressor behavior, even beyond the simple threshold violation. And here it's important to ensure reliable in monitoring. Those thresholds must be maintained carefully over time to avoid also too many false alarms. But for this challenge, we have developed a new algorithm to make the threshold management redundant and also reducing the manual effort and improving the detection accuracy. The algorithm starts by learning how the compressor is typically operated during a training period of 2 to 3 months. And in this phase, it builds a model of expected behavior based on the collected data. And once the learning phase is complete, the algorithm goes live and it continuously compares the actual measured values against the expected values for each segment. And these comparisons generate then a deviation heat map, highlighting like both the minor and the major deviations. And this approach allows us to detect the abnormal patterns early and patterns that traditional threshold-based methods would have missed. For example, a falling valve opening signals. As a result, operators can now focus on meaningful changes in the compressor behavior. And here, what are the key benefits? The manual threshold, tuning, fewer false alarms, and also reduced maintenance efforts for the operators. Now, let's look at the real-world example. We installed the UpDetect on a customer-connected compressor on the next slide. So then, in the next slide, after a long period of stable operation, the system detected a change in vibration behavior, specifically in the early and late segments of the cycle. You can see here the red strong increase. Over the time, the signal gradually intensified until exceeded the initial thresholds, triggering an alarm from the system. The system didn't just raise the alert, it also identified the likely failure mode and provided an actionable recommendation. In this case, you can see the issue was the head and discharge valve. And based on the timing and pattern of the vibration increase, the system gave this recommendation. Then the customer kept the machine running, but proactively ordered already the replacement valves to be ready in case of any failures. And then 2 weeks later, his other system detected also a rise in temperature and a drop in performance. And then he decided, okay, now it's time to open the compressor, and the head and discharge valve was exchanged. And also as predicted, the head and discharge valve was damaged. And thanks to the early warnings from our UpTime system, the customer minimized the unplanned downtime and avoided costly emergent repairs, or any further damage would have maybe affected this broken valve. However, not every customer has the budget, of course, for a full condition monitoring system, and that's also why we have alternative ways to improve the compressor maintenance. And this is why we'll hand over now to Vitaly again.
Thank you, Philip. Of course, these digital and monitoring solutions, they represent a very good basis for us to understand the performance of asset and bring improvements in maintenance and the design of components. Here we can see typical examples where we use these systems actively, support on the root cause analysis, bad actor identification, monitoring can provide a very good data. Quantitative performance analysis of compressor, capacities, temperatures, pressures, and power consumed, as well as individual components such as valves, sealing system, piston rings, for example. We take this data and we use this data either to redesign and improve component that is a sufficient and an important part on our activities, or we do analysis of maintenance interventions on a compressor. Very typical example is comparison of machine condition before and after maintenance, and as one extremity in this case is major interventions such as turnarounds, major overhauls, where system is particularly used also in advance to get an understanding on the scoping of intervention, to see which operations are really necessary. And it's true, compressors have different operating age, different level of equipment, and not always have monitoring systems. And in some cases, we bring it to the compressor to install temporary for specific events as a part of our on-site condition assessment. And one very particular example I would like to present now, how it was done for after maintenance analysis after a big overhaul. And compressor, which is in the discussion, it's a large 5 megawatt machine installed on a so-called LDPE plant, or low density polyethylene production plant. It serves as a hyper or secondary compressor. So the duty of a machine is to supply gas, which is compressed to quite a wide range of very high pressures from 2000 to 3500 bar to the reactor for polymerization. And this is a very critical machine. It's very common that such machines have no backup unit. And this particular machine, it was 40 years old machine. It has no dedicated monitoring system installed on it. And the task was a large overhaul of this machine when compressor was effectively refurbished and rebuilt on a regrouted foundation. I would like to leave aside now maybe technicalities of overhaul itself and discuss commission and a startup phase. So it's very common for such plants to have a time pressure factor, and the startup and commissioning is not an exclusion. It has to be done on a very timely manner. And to facilitate this, it was taken a decision to bring a temporary monitoring system with all capabilities like vibration measurements on the crosshead guides, on a cylinder, in a time domain, indicator pressure, and these signals have been synchronized with a crank angle position by a trigger sensor connected. So this was the scope of the system, and activity of such scale, when compressor had to be rebuilt, of course, is very complex. Many things have been done. And on the one morning, compressor has been started. First, it starts without a load, then pressure difference across compressor slowly increases. And approximately 20 minutes later, we have been seen in the system a high vibration peaks. On the right side, you can see two screenshots, top being before this peak appearance, and second lower side is after, which have been accompanied by a very strong noise. So compressor have been stopped very quickly, and now was a need to discuss and analyze what would be the next steps. And it would be virtually impossible in a very short time without a system to identify from where that noise was coming. So a larger inspection would be required, delaying the startup of the production, which was not, of course, an optimal scenario. But having a system at hand during the commissioning, we could quickly pinpoint and localize that high vibration is coming from particular crank, number 4, from the cylinder. And we also, with information assembled, could make a judgment what could be a possible cause of it. This is related to the increase in pressures. So looseness of certain components have been suspected. So the next decision was taken to inspect specifically this crank and open the cylinder on the machine. And the results and the little explanations are presented on the next slide with maybe first to understand that the mounting system of a liner is quite specific on this machine. It is clamped by a system of liner itself, pressing cages, packing, and it actually has a very high dimension and tolerances. And the distance is compensated by a distance shim. And it was found out that on one of the cylinders, in particular the cylinder number 4, distance shim had to be adjusted to accommodate earlier machining of a packing housing. So it was very quickly understood that was a looseness, exactly as suspected, eliminated also very quickly, and on a quantitative feeling, let's say, failure was eliminated in a couple of hours, while without system it would require 1 up to 2 days out of 365 days per year operating plant, which of course would not be positively impacting economic indicators of this plant. So that was really helpful. One particular example how such systems can benefit even on a temporary measurement to increase availability of the unit. And with this remark, I would like to hand over to Daniela for conclusions.
Thank you, Philip and Vitaly, for sharing your valuable insights. Now, let me briefly summarize. So we have heard how the maintenance strategies evolved from reactive fixes to preventive schedules, then condition-based monitoring, and finally, predictive maintenance, and how data and artificial intelligence are driving this shift towards more and more prediction. We also saw how monitoring solutions support on-site operation teams by sending also notifications when a machine alarm occurs, along also with recommended actions. And that always backed up by OEM experts who are available for clarifications. Based on the data, they also perform monthly health checks if required. And finally, if no monitoring is installed, Vitaly demonstrated how on-site diagnostics and assessments can increase compressor uptime. So we hope that those insights were of value to you. Of course, more information is also available on our website under digital solutions. You can find the link here. And as I said, we are always very happy to get feedback or topic ideas. So we have just posted a link into the Q&A section where you can give us your feedback and also some ideas for future webinars. Yes, so if you found the webinar valuable and you would like to stay informed, also here we have the possibility to get registered. So you can leave also your name on our form and you will get informed well in advance when we have future events. So now we are at the end, and many thanks to our audience for being with us today. And of course, to Vitaly and Philip and the team in the background who made this possible. The link to the recording will be available on our website, and I will be also shared with you in a separate email and on social media. Please feel free to reshare with colleagues that might be interested in the session of today. Now I wish you a great day, and until next time, goodbye.